Hello and welcome to this video. So this is a lecture for chapter 1 of Mechanics of Deformable Solids, CE 108. So in this chapter what we are going to see is a review of what you need to remember from the statics class for CE 108. So we're going to review a few things of the key definitions or the key concept that you need to remember for this class. So in this first part, we are going to first have a brief review of the different types of forces, external forces that can be applied to a material. So the goal of this chapter today, again, is to review what you have seen from statics, and the more specific goals is to relate the force that we know. So the known forces. So those are going to be the external forces. So that those are typically what you know. This is what is applied by an external agent to a material or by one material to another material. So this is what is known. And we want to find the relationship between what is known, those external forces, to what is not known, to what is unknown. And the two things that are unknown in this case, first are what are the reaction from the support if a material, if a body is at equilibrium, if you apply an external force, and if this body is at equilibrium, then it means that there is a reaction from a support that maintain this body at equilibrium, and that is going to counterbalance the external forces. So we need to be able to calculate the unknown forces that are applied by the support. And then the second thing is that if you apply some external forces, you will induce some internal load within the material. And again, this load is not a priori known. So it's something that is unknown. And this internal load is what is going to govern the risk of fracture of a given material. So if we are able to predict the internal load that arises within a material that is subject to some external forces or some external moment, then we can predict if this material is going to break or not. So those are the two things that we are going to start reviewing in this chapter. So to relate how we can go from the forces that are known, the external forces, to the forces that are unknown, that is to say the reaction from the supports and the internal loads, the forces that act inside the material itself. And in this first video, we are going to start first with a review of the known forces, the different types of external forces that can be applied. And then in the next video, we will move to the unknown forces. So let's start with the different types of known forces that you might be experiencing or interacting with in this class. So the first types of known forces, which is maybe the most simple, are concentrated forces. So when I say concentrated forces, the definition of a concentrated force is that you have a given member and you have a force that is applied on this member, and this force is applied at only a given point of this material. So that's a point contact force. And in this case, the idea behind the concentrated forces is that the force is applied on a single point of this material. And the definition of a point is a given position, so a given location within this material, and a point doesn't have any surface. A point is a location with a zero surface. That's just a single point at a given location, which doesn't have any surface or no area. So this concept of a concentrated force is actually an abstraction. That's a model, because you can never have a force that is applied at a single point. A force is always applied on at least a small area, even if you have a very sharp object, and if you apply a given force with this sharp object to another materials, necessarily the force that is going to be applied by the sharp object is not going to be exactly it's not going to be transmitted to the material over a single point. It's going to be necessarily transmitted over an area, potentially a very small area of contact, but it cannot be a single point. It's only applied over an area. But if this area of contact is very small as compared to the size of the materials, then we can assume as an approximation that this force is applied at a single point. And in that case, we can refer to that as a concentrated force. The other types of force that can be applied is if we cannot assume that it's applied at a single point, then it's going to be applied over a given surface. And in this case, the other types of force that you will experience in this class are the distributed loads. So in this case, in the case of distributed loads, the load is not applied at a given point, but it's applied over a given surface. So in this case, the types of distributed load that we'll be interacting with, we will be representing it as follows. So if you have a given material like this, a given body, and this body, for example, has a length L, so we can look at the position of this body according to an axis X. In this case, we can represent a distributed load like this, where in this case the quantity that we will be defining is W of X, where W is the force per unit of length. It's the force that is applied of materials, but since this force is not applied at a given point, but it's applied over a given area, then you cannot define the force at a single point, because in this case, since the force is distributed over an entire surface, at a single point, this force would actually be zero. This force is just distributed over a large surface. So if you look at a single point of this surface, since there is no area, the point doesn't have any area, then at this point, the force would be zero. There is only a force when you have a surface. So in this case, the quantity that matters is not the magnitude of the force at a given point, but it's the magnitude of the force per unit of length. So in this case, we define the quantity W of X, which is the force per unit of length. So in this case, if you have a concentrated force, the unit of a force is in Newton, or which is the unit of a force. In this case, the unit of W of a distributed load, since it's the force per unit of length, then its unit is in Newton per meter. And once you have a distributed force, one thing that we commonly want to do is to calculate what is the resultant force that is equivalent to this distributed force. So in this case, the resultant force is the sum of all this distributed load. And in this case, the two things to remember is that the resultant force that is equivalent to a distributed load, so the resultant force is going to be the sum of the entire distributed load. And the two things to remember is that the resultant force that is equivalent to a distributed load is applied. If you want to define a force, you need two things. You need to know at which point is it applied and what is the intensity of this force. So in this case, it is going to be applied at the centroid. The centroid of what? The centroid of the load diagram. So if you define this as the load diagram, then you look at what is the centroid, the geometrical centroid of this load diagram, and that's going to be the point at which the resultant force that is equivalent to the distributed load is going to be applied. So it's going to be applied at the centroid of the load diagram. So that's the first thing. That's about the point at which the resultant force is applied. And the second thing is about the intensity of the force. And the intensity of the force is going to be given by the area of the load diagram. So you take the load diagram, you calculate its area, and its area gives you the intensity of the force. So this is the area of the load diagram. So another way of writing this more mathematically speaking is that the force is the area of the load diagram, and the load diagram is the integral of the distributed load over between 0 and L, over the length over which the distributed load is applied. So you take the load diagram, you integrate it between the beginning and the end of the position over which this load is applied. That's the integral, and that gives you the intensity of the force. That being said, in this class, we will typically not have to calculate explicitly these types of integral, because we will focus on two types of distributed load. The first type will be rectangular loads, where the loads in this case is the same over the entire length of the member. So in this case, if you have a given member like this, that with a length that goes between 0 and L over the axis X, and if the load is constant, and usually when it's constant we can write it W naught, then in this case the load diagram is simply a rectangle, which means that in this case the centroid of this rectangle is going to be the middle of the member. So the force will be applied at X equal L over 2, and the intensity of this force is going to be the area of the load diagram, which in this case is the area of the rectangle, which is simply W naught times L. So in this case, when you have a rectangular load, you don't need to worry about calculating the integral. That's just the area of the rectangle. And then the second types of distributed load that we will experience in this class are triangular loads. So if you have a load that is like this, that increase linearly with respect to the position X. So in this case, same thing, the load is going to be applied at the centroid of the load diagram. So in this case, if we define W naught as being the value of the load at X equal L, so then we can do two things. We can see where the centroid is, and we can calculate the magnitude of the force, of the resultant force. So when it comes to centroid, so in this case, that's simply the load diagram is a triangle. So the centroid is going to be at 2/3 from the summit of the triangle. So the resistant force will be applied at 2L over 3, so at 2/3 from the summit of the triangle, and the intensity of the force will be the area of this triangle, where the area of the triangle is half of a rectangle, so it's the area of the rectangle W naught L divided by 2, since this is a triangle. And those are the only two types of distributed load that we will be seeing within this class. So one thing in common between distributed force and concentrated forces is that those are forces that are applied by a contact. You have either an external agent or a material that is going to apply a force on another body by means of a contact. In this case, the force is applied because you have one thing that touches something else. Those are contact forces. Another type of forces that does not require any contact are the body forces. So body forces are forces that are not applied through a surface, so it doesn't require any contact between one material and another. So it's a no contact force. It's not applied through a surface. It's applied directly to the bulk of the material itself. It's applied simultaneously to every point the material is made of. So some example of body forces are, for example, gravity. Gravity is the force that is applied between two masses that are at a given distance from each other. In this case, gravity does not require any contact between those two masses. Or another example are electromagnetic forces, forces that are between charges, for example, or forces resulting from the application of a magnetic field. So in this case, those are forces that again are applied directly to the bulk of the material and do not require any contact. So they are not applied through a surface. In the case of CE108, the types of body force that we will mostly care about is the force of gravity, especially the force of gravity due to the Earth. So in this case, if you have a given body, the Earth will apply a given weight to this body. In this case, just like any force, if you want to define what this force is, you need two things. You need to know at which point this resultant force is applied and what is the magnitude of the resultant force. So in the case of gravity, the resultant force is applied at a given point, which is the center of gravity of the body. So this is the G, the center of gravity of the body, and the magnitude of the force. The force is in this case equal to the mass of the body times the gravitational acceleration G. So another type of external load that we are going to experience in this class are moments. So the way we can define a moment, so we are going to define it as follows. We are going to say that a moment is the propensity for a force. So a moment is going to be a consequence of a force. So it's the propensity for a force to make a body rotate. So moments tend to make body rotate. So that it's a propensity of a force to make a body rotate. And the last thing that is important is that it's going to rotate about a given point. So if you consider a given object like this, a given body, and if you apply a single force like this, so typically a force will make this material be translated in the direction of the force. But another thing that force can do is that they can make body rotate about a given point. And that's what is going to be captured by the moment. So let's take an example. So if you consider a body like this, if you have a given force, then this force can potentially make this body rotate about a given point O. So if you want to calculate the moment of the force about this point O, so the moment depends on the force that you are considering. Different force will apply different moments, but it also depends on the point about which you are calculating the force. So the force always, the moment always depends on the point about which you are calculating this moment. So to calculate the moment, you need to define two things. First, you need to define what is the arm of the force. The arm of the force gives you the direction of the force. So the force is this is the line of action of the force. You need to define the line of action of the force. So the line of action of the force is the direction of the force. So since the force is a vector, it has a given direction, and this direction is the line of action of the force. And then the second thing that you need to define is the arm of the force. The arm of the force is the orthogonal distance between the point about which you want to calculate the moment and the line of action. So you take the orthogonal projection of the point about which you want to calculate the moment to the line of action. You calculate the orthogonal distance between the line of action of the force and the point about which you want to calculate the moment, this orthogonal distance is going to be what we call typically D, which is the arm of the force. So the arm of the force depends on the point about which you are calculating the moment. So once you have defined those quantities, then you can calculate the moment of the force F about the point O. So the moment always depend on the point about which you are calculating this moment. So we need, typically we are going to write it like this. If you want to calculate the moment of F about O, you're going to write this MO to indicate that this is the moment about O. In this case, the moment of a force about the point O is going to be the product of two things. The product of first, the magnitude of the force. So you take the magnitude of the force F, and you need to multiply this by the arm of the force, where the arm of the force is the orthogonal distance between the point about which you are calculating the moment and the line of action of the moment. So if you calculate this, you get the arm of the force, and the product of the arm of the force times the magnitude of the force gives you the moment of F about O. So now the second thing is that once you have this magnitude of the moment, the second thing you need to worry about is the sign. So you can have either positive or negative moments depending on whether they make body rotate anti-clockwise or clockwise. So there is no specific reason of why a moment should be positive or negative, because if you think about a clockwise moment or an anti-clockwise moment, there's no reason that one should be positive and the other one should be negative. But we need to agree, we need to adopt a single convention so that we can make sure we can speak the same language and have consistent results. So in this case, this is just a sign convention. This is not a sign that specifically makes sense or that has any kind of physical meaning, but we need to decide what we are going to call a positive moment and a negative moment. Again, those are perfectly symmetrical with respect to each other and they have no different physical meaning, but we need to distinguish what we are going to call a moment that tends to make a body rotate clockwise with respect to a moment that tends to make a body rotate in an anti-clockwise fashion. So the sign convention that we are going to be using in this class is as follows. If you have a given body like this and you apply a force like this, so this force will tend to make the body rotate anti-clockwise about the point O. And in this case, this is what we are going to call by definition or by convention a positive moment. While on the other hand, if you have the opposite cases where you have a body like this and you apply a force like this, then this force in this case is going to tend to make the body rotate in a clockwise way about the point O. And in this case, that's what we are going to, by convention, refer as a negative moment. So in this case, positive moment make the body rotate anti-clockwise, and a negative moment tend to make the body rotate clockwise about the point at which you want to calculate this moment. So in this case, what we are using is what we are calling the right hand rule. So the idea being that if you use your right hand and you put your thumb pointing towards you, then the direction of your finger gives you the direction of a positive moment. Your finger points towards an anti-clockwise direction, and this is what is giving you the convention for a positive moment. Be careful just if you are using so very commonly you have to remember what is a positive moment and a negative moment. So make sure you are always using your right hand to remember that. Don't use your left hand, especially if you are going to be during an exam and you are going to be using your right hand to write stuff if you are right-handed. then make sure if you are using your right hand to hold your pen, make sure you are not using your left hands to remember what is the definition of the convention for the positive moment. Make sure you are always using your right hand. So those were the forces that we typically know. Those are the external forces that are applied to material. Those are the ones that we know. Those are the ones that external agents or other materials apply to a given material. Those are the forces that you know. So now what we're going to see in the next video is what are the forces that you don't know. What are the unknown forces? And those unknown forces, since we don't know them, those are the forces that we typically want to calculate in terms of the known forces.